Okay, let's unpack this. Have you ever looked at a complex system like Kubernetes and found yourself wondering, how on earth do the world's biggest tech companies, the FAANGs, actually make this work at such a mind-boggling scale? Well, today we're taking a deep dive into exactly that. We've got a fantastic stack of sources covering everything from the foundational concepts of containers to the intricate dance of service meshes, all designed to give you a true shortcut to understanding how these complex systems are not just built, but robustly secure.
And what's truly fascinating here is that we're going beyond mere definitions. Our mission is to connect the dots, showing how these individual building blocks aren't just features, but crucial pieces assembled into highly resilient, production-grade architectures. This isn't just about knowing what a pod is, it's about grasping what it really takes to make thousands of microservices operate seamlessly and securely at a global scale.
Let's start right at the very core then, Docker and containerization. From your perspective, what was the single biggest revolution Docker brought that enabled this kind of scale and predictability we now see at the FAANG level?
That's a great question because Docker truly was a game changer. I think the biggest revolution was its concept of OS-level virtualization. Think about it like this. Traditional virtual machines virtualize the entire hardware, meaning each VM needed its own full guest operating system, heavyweight stuff.
Right, lots of overhead.
Exactly. Containers, however, just virtualize the operating system layer, sharing the host OS kernel. And the core insight here for building at scale isn't just efficiency, although it's part of it. It's how this lightweight shared kernel approach fundamentally enabled the concept of immutable infrastructure.
Ah, immutability, key concept.
Huge. You get unparalleled portability, that whole build once, run anywhere, promise and consistency across every single environment. Staging, production, developer laptops, that just eliminates the dreaded, it works on my machine problem, which is, well, it's a nightmare when you're managing hundreds or thousands of developers.
Couldn't agree more. So when we're talking about Docker, there's a key distinction everyone needs to grasp, the Docker image versus the Docker container. Can you break that down for us, maybe especially highlighting what makes that layered image architecture so powerful?
Absolutely. Think of the Docker image as your read-only blueprint. It's like a precise recipe for your application and its entire runtime environment, everything it needs. You build it once from a set of instructions, the Docker file. And what's really ingenious is how images are constructed in layers. Each instruction in your Docker file potentially creates a new immutable layer.
Immutable layers.
Right. This layered architecture means amazing efficiency. Only change layers need to be rebuilt or pulled, saving massive amounts of time and disk space, network bandwidth.
Got it. So the image is the blueprint.
And the container is the actual running instance of that image. It adds a thin, writable layer on top for any runtime changes, but importantly, containers are designed to be ephemeral.
Disposable.
Ephemeral, meaning temporary. Exactly. And immutable. If the container dies, any data stored directly inside that writable layer is gone. Poof! Which is precisely why you must use volumes for persistent storage. That's non-negotiable for real applications.
Speaking of building images, the Docker file is that instruction manual for these blueprints. What are some of the most crucial ingredients in that recipe? Maybe some best practices that really make a difference for efficiency and security at scale.
Okay, the Docker file is critical. You'll always see from to specify your base image and pro tip. Choose small, secure base images whenever possible. Alpine, distroless, that kind of thing.
Smaller is better.
Definitely. Then workdir sets your working directory inside the image, and copy wire ADD, get your application code and files into the image. Run executes commands during the build process, like installing packages. Expose documents the ports your application listens on, and CMD your entry point to find what command actually runs when your container starts up.
Okay, those are the basics. What about best practices for the big leagues?
Right. Always use a .docker ignore file. You're just like a .git-ignore for your Docker builds, keeps unnecessary source code, build artifacts, large files out of the build context, speeding things up and reducing image size.
Makes sense. And you mentioned security.
Crucially, at FAANG scale, multi-stage builds are basically non-negotiable.
Yeah.
You build your app in one stage, let's say, using a full JDK or Go compiler image. Then in a second final stage, you start from a minimal base image and only copy the compiled artifact, the JAR file, the binary from the first stage.
Ah, so you'd ditch all the build tools.
Exactly. You ditch the compilers, the SDKs, everything not needed at runtime. This drastically reduces your final image size and, more importantly, your attack surface. It's a massive win for security and deployment speed.
So Docker provided these essential building blocks. Now, before Kubernetes became, the undisputed heavyweight champion, Docker had its own native orchestration tool called Docker Swarm. I remember it being known for its simplicity.
It was, yeah.
What did Swarm get right, and then why did Kubernetes ultimately win out so decisively?
Docker Swarm certainly offered ease of use. It was very quick to get a cluster up and running, especially for simpler deployments.
Hmm.
Relatively straightforward. However, if we connect this to the bigger picture, why Kubernetes won, well, it emerged as the industry standard due to its vastly larger ecosystem, its incredible extensibility with custom resource definitions, CRDs, which we'll definitely talk more about.
Okay.
A truly declarative API, and far more advanced features for networking, storage, and application lifecycle management. For almost any serious, large-scale production environment, especially those mimicking Epsilon complexity, Kubernetes just offers much more power and flexibility. It became the superior choice.
So Kubernetes needs something to actually run the containers, right? It doesn't do that itself.
Correct. Kubernetes relies on container runtime. This is the low-level component that actually manages the container lifecycle, pulling images, stopping containers. Container is now the de facto standard, originally spun out of Docker itself. CRIO is another popular alternative specifically designed for Kubernetes.
And wasn't there a big change recently with Docker Shim?
Yes, exactly. It's important to be aware of the deprecation of Docker shim in Kubernetes version 1.24. Kubernetes used to talk to Docker through this shim, but now it talks directly to runtimes like container via the Container Runtime Interface, or CRI. This just highlights Kubernetes' ongoing evolution towards more standardized modular components. It's cleaner.
Okay, so the runtime handles the container execution, but how do we actually configure these containers once they're running in Kubernetes? Especially for non-sensitive data, things like API endpoints or feature flags.
Well, for simple settings, good old environment variables are common. You can set them directly in a pod definition. But for more dynamic or structured non-confidential data, Kubernetes gives us config maps. A config map is precisely what it sounds like, a dedicated object for storing non-confidential configuration data as key value pairs.
And how do applications actually use these config maps?
The really powerful feature, especially for dynamic environments, is the volume mount of config map. You create a config map object, then you define it as a volume source in your pod definition, and finally, you mount that volume into your container at a specific path.
So the config data appears as files.
Exactly. The keys from the config map appear as files inside your container's file system. And here's the cool part. If you update the config map object in Kubernetes, the kubelet automatically updates those files inside the running container.
Without restarting the pod.
Correct. Your application just needs to be smart enough to detect those file changes and reload its configuration. This enables live config updates, which is super useful.
With our containers configured and ready, how does Kubernetes manage them at scale? Let's zoom in now on the smallest deployable unit, the pod. I hear a lot of people, especially newcomers, mistakenly talk about deploying containers directly to Kubernetes. Can you clarify why that's not quite right and why pods are the fundamental unit?
That's a critical distinction to make, absolutely. You should always emphasize that you deploy pods, not raw containers, to Kubernetes. A pod is the smallest, simplest deployable unit in the Kubernetes object model. Think of it as a wrapper or an envelope.
An envelope for containers?
Pretty much. It encapsulates one or more tightly coupled containers, their shared storage resources, volumes, a unique network IP address they all share, and options for how those containers should run. The reason pods exist is that they provide the atomic unit of scheduling and networking. All containers within a single pod are always scheduled together onto the same node, and they share the same network namespace.
Shared network namespace, meaning they can talk over localhost.
Exactly. They can communicate via localhost, and they share the same IP address and port space. This is essential for certain patterns, especially the sidecar pattern.
And that leads us directly to multi-container pods, often using what we call the sidecar pattern. This seems like a really common pattern for these FANG level architectures. Can you give us some concrete examples of when and why you'd use a multi-container pod?
Oh, absolutely.
Yeah.
This is where pods really shine beyond just running a single application container. The sidecar pattern is pervasive at scale. Think of examples like the Istio Envoy proxy, which we'll definitely dive into later. It runs as a sidecar container right alongside your main application container.
Intercepting traffic.
Precisely. It intercepts all inbound and outbound network traffic, adding sophisticated service mesh capabilities like mutual TLS, traffic management, metrics, traces, all without your app even knowing it's there. It's transparent.
Wow, that's powerful. Any other examples?
Sure. Other common sidecars include log shippers like Fluent or Vector. They sit there, read log files from a shared volume mounted into the pod, and forward them to your central logging system. Or you might have key or certificate rotators,
Yeah.
a sidecar that fetches secrets dynamically from something like HashiCorp Vault and places them in a shared memory volume for your main app to consume securely.
So the shared network and shared volumes within the pod are key enablers.
They're fundamental to the sidecar pattern. And remember, pods are inherently ephemeral. If a pod dies, maybe the node fails or it gets evicted,
Hmm.
it's not resurrected on the spot. Instead, a new replacement pod is created by its managing controller, like a deployment.
Right, that ephemerality. Treat them like cattle, not pets.
Exactly. It's a core design principle for building resilient, self-healing systems in Kubernetes. Don't rely on individual pods sticking around.
So pods are the building blocks, but they come and go. How do you keep your application running reliably, scale it up and down, and manage its lifecycle, especially when you potentially have thousands of them?
That's where Kubernetes workload objects come into play. These are higher-level objects that manage pods for you. They define the desired state for your applications and abstract away the complexity of managing those individual ephemeral pods.
Okay. For stateless applications like typical web servers or APIs, the primary manager is the deployment. This is probably what most people interact with first when they start with Kubernetes, right?
Exactly. A deployment is the workhorse for stateless apps. It provides declarative updates for pods and the underlying replica sets it manages. You define your desired state in the deployment YAML, say, I want 5 replicas of my web server running image version 1.2, and the deployment controller continuously works to ensure the actual state matches that desired state.
And this handles updates too.
Yes, this is how you achieve zero downtime rolling updates. When you update the image version in your deployment, the controller gradually terminates old pods and creates new ones based on the new spec. It ensures a minimum number available throughout the process.
Can you control how that rollout happens? Like how fast?
Absolutely. You can fine-tune the rollout strategy with parameters like max surge, which controls how many extra pods can be created above the desired count during an update, and max unavailable, which defines how many pods can be unavailable at any given time during the update. It gives you good control over the speed versus safety trade-off.
And what about replica set? It often comes up in conjunction with deployment, sometimes confusingly.
Yeah, it can be confusing. A replica set's sole job is simpler. It's just there to maintain a stable set of replica pods running at any given time. It ensures you always have the specified number of identical pods running. But here's the crucial point, and it's something you should really emphasize. You should almost never create a replica set directly. Always use a deployment,
Why is that?
because the deployment manages replica sets for you. When you do a rolling update, the deployment creates a new replica set for the new version and gradually scales it up while scaling the old replica set down. This mechanism is what provides all the crucial rolling update, rollback, and declarative lifecycle management functionality that you absolutely need for any real application. Replica sets alone don't give you that.
Got it. Deployments for stateless apps. Manage replica set. Okay, deployments handle stateless applications well. But what about stateful applications like databases or distributed message queues? That feels like a whole different ballgame at scale.
It absolutely is. Stateful applications have different requirements. Stable identity, persistent storage tied to specific instances, ordered deployment. This is where the stateful set comes in. While deployments are perfect for stateless apps you can scale up and down arbitrarily, stateful sets are specifically designed for stateful workloads like databases, think PostgreSQL clusters, distributed key-value stores, like etc. itself, or message brokers, like Apache Kafka clusters.
What makes them different? What are the key features?
The key difference is that each pod managed by a stateful set gets a stable, unique identity. It gets a predictable and stable network hostname like app-0.my-svc, app1.my-svc, and so on. And crucially, each pod instance gets its own unique persistent volume claim, meaning its storage is tied directly to its identity.
So if app0 restarts, it comes back as app0 and gets the same storage volume back.
Precisely. Even if it gets rescheduled to a different node, it retains its identity, app0, and reattaches its dedicated storage volume. This is absolutely critical for distributed stateful systems where data locality and instance identity matter. Stateful sets also enforce ordered and graceful scaling and updates. Pods are created, updated, or deleted one at a time in order 0, 1, 2. This predictable ordering is often essential for maintaining data integrity and quorum in clustered stateful applications. Deployments just can't provide that level of ordered control.
That makes sense for databases and things like that. What about applications or agents that need to run on every node in your cluster, or maybe just a specific subset of nodes, like monitoring agents or log collectors?
For that specific use case, you use a daemon set. A daemon set ensures that a copy of a particular pod runs on all, or a selected subset of, nodes in your cluster. As nodes are added to the cluster, the daemon set controller automatically adds the pod to the new node. When nodes are removed, the pods are garbage collected.
What are some common examples?
It's perfect for cluster-level utilities. Things like log collectors, maybe Fluent or a Splunk universal forwarder that need to grab logs from every node, or monitoring agents like the Prometheus node exporter, which collects node-level metrics. Even the underlying CNI network plugins, like Calico or Cilium node agents, are often deployed as daemon sets to ensure network functionality on every node.
Okay, so we have deployments for stateless, stateful sets for stateful, and daemon sets for node-specific tasks. What about one-off tasks? Things that need to run, do their job, and then finish, like a database migration script.
That's where Job and cron job come in. A job creates one or more pods and ensures that a specified number of them successfully run to completion and then stop. They're designed specifically for finite tasks that have a clear end. Think batch processes. Running a database schema migration once during a deployment, performing a one-time data transformation, or taking a backup. Once the pods finish successfully, the job is complete.
And cron job builds on that.
Exactly. A cron job takes the job concept a step further by creating jobs on a repeating schedule. You define the schedule using the familiar cron syntax. The star, star, star format.
Right, like for nightly tasks.
Precisely. Perfect for things like nightly backups, generating scheduled reports, sending out periodic emails, or running data cleanup tasks automatically on a regular basis. It just manages the creation of job objects according to your schedule.
And finally, one more workload type. Before our main application container even kicks off inside a pod, what if we need some prerequisite setup to happen first? Maybe wait for a database to be ready or initialize some configuration?
That's the exact role of init containers. These are special containers defined within a pod specification that run to completion before your main application containers in that pod are started. They run sequentially, one after the other. Each one must complete successfully before the next init container or finally the main app container can start.
What happens if one fails?
If an init container fails, the kubelet restarts it according to the pod's restart policy until it succeeds. The main application won't start until all init containers have completed successfully.
What are they used for?
They're incredibly useful for setup tasks that must complete first. Common examples include waiting for dependent services, like a database or another API, to become available before the app starts, running database migrations or schema initializations, preparing data directories or downloading necessary files, or setting specific file permissions that the main application might not have the rights to do. They can share volumes with your main application, making them perfect for these kinds of preparatory steps.
Okay, those workload objects give us a lot of control. Now that we know the core building blocks, pods, and the controllers that manage them, let's peek under the hood at the brain of Kubernetes, the control plane. I like to think of the Kubernetes cluster as a hotel. If so, the control plane is like the hotel management, the front desk, the managers, the booking system. They don't carry the luggage or clean the rooms themselves, but they decide which guest pod goes to which room, node, handle reservations, scheduling, and ensure the whole hotel is running smoothly. Expert, let's start with the central nervous system of that management team, the Kube App Server. What's its role?
That hotel analogy works perfectly. The Kube App Server is indeed the central hub, the front door, the main API endpoint for the entire cluster. Everything talks to it. Crucially, it's the only component that talks directly to, etc., which is our persistent storage, the single source of truth for the cluster state.
Only the API server talks to, etc.
Correct. Its role is to validate and process all incoming requests from users via kubectl, from controllers, from kubelets. It manages the state persistence and etc., and it handles authentication, authorization, typically via RBAC, role-based access control, and admission controllers, which can modify or validate requests before they're persisted. Every single interaction with the Kubernetes cluster flows through the API server.
And you just mentioned etc. as the single source of truth. It stores the state. How exactly does etc. maintain that consistency, especially in a distributed system where things can fail? And why is its watch feature so foundational to Kubernetes' whole declarative model?
Right, etc. is a consistent, distributed, highly available key-value store. It's designed for exactly this purpose. It achieves its high availability and consistency using the Raft consensus algorithm. Essentially, this ensures that all the etc. nodes in the cluster agree on the state before any change is committed. It prevents split-brain scenarios.
Okay, Raft handles consistency. What about that watch feature?
The watch feature is perhaps its most critical contribution to Kubernetes architecture. Any component in Kubernetes can ask the API server to watch for changes on specific resources, which are stored in etc. When a value in etc. changes, say a deployment object is updated, etc., immediately notifies the API server. The API server then, in turn, notifies any other Kubernetes component that is registered a watch for that object type.
So controllers get notified instantly.
Exactly. This watch mechanism is the very foundation of Kubernetes' reactive declarative model. You declare your desired state in the YAML file, you kubectl apply it, the API server writes it to, etc. The relevant controller, which is watching for changes, gets notified immediately and then starts taking action to reconcile the actual state of the world to match that desired state. It's this constant watch reconcile loop that drives everything.
Okay, so once a pod is created via the API server and stored in, etc., something has to decide which node it should actually run on. That's the kube scheduler's job, right? How does it make those decisions, especially in a large, potentially diverse cluster with different machine types? And what tools do we as operators have to influence its choices?
That's precisely right. The kube scheduler's sole responsibility is to assign newly created pods that don't have a node assigned yet to a suitable node. It constantly watches the API server for these unscheduled pods. Its decision process is typically a two-phase approach. First, there's filtering. It filters out any nodes that absolutely cannot run the pod. Maybe they don't have enough resources, CPU memory, don't match required labels, have taints the pod doesn't tolerate, etc.
Okay, narrow down the options.
Exactly. Then, phase two is scoring. For the nodes that passed filtering, the scheduler scores them based on a set of priority functions, things like preferring nodes with fewer existing pods, nodes that already have the required container image cached, or nodes that satisfy affinity rules. The node with the highest score wins, and the scheduler assigns the pod to it.
Can we nudge it in certain directions? Tell it what we prefer.
Oh, absolutely. Kubernetes provides several powerful mechanisms to influence the scheduler's decisions. For basic hard requirements based on node labels, there's node selector, simple key value matching. For more advanced expressions and preferences, there's node affinity. This lets you define rules like must run on nodes with SSDs, hard requirement, or prefer to run on nodes in availability zone USEAST 1A, soft preference.
What about placing pods relative to other pods?
Good question. For that, you use pod affinity and pod anti-affinity. Pod affinity helps you co-locate related services on the same node or in the same zone for better performance or reduced latency. Pod anti-affinity is crucial for high availability. It helps you spread replicas of a service across different nodes or zones to avoid single points of failure.
And you mentioned taints.
Right. Taints are applied to nodes, and they act as a kind of repel mechanism. By default, pods won't be scheduled onto a tainted node unless they have a corresponding toleration. This is often used for dedicating nodes to specific workloads or preventing general workloads from landing on control plane nodes. Using all these mechanisms, effectively affinity, anti-affinity, taints, tolerations, is really key to optimizing resource utilization and resilience, especially in large heterogeneous clusters.
Beyond the scheduler assigning pods, we have the kube controller manager. This is where the magic of those control loops we talked about truly comes to life. Can you explain that concept in a nutshell? What does this manager actually do?
The kube controller manager is essentially the orchestrator of many of Kubernetes' core control loops. It runs multiple different controller processes bundled together in a single binary for efficiency. Think of it as a team of persistent observers and actors. Each individual controller within the manager has a specific job. It watches a particular type of Kubernetes object, like deployments, replica sets, nodes, services, etc., via the API server's watch mechanism. It compares the observed actual state of those objects with the user's desired state, which is stored in etc. via the API server. Then, if there's a difference, the controller takes actions through the API server to reconcile that difference.
Can you give an example?
Sure. The replica set controller. You declare, I desire 3 replicas of my web server pod in a deployment, which creates a replica set. The replica set controller watches that replica set and the pods it manages. If it observes only 2 pods are currently running, it will immediately tell the API server to create 1 more pod to match the desired state of 3. It's this constant loop. Observe, compare, act.
And the controller manager runs lots of these loops.
Yes, many core ones. The deployment controller manages replica sets for rollouts. The node controller monitors node health and responds if nodes become unreachable. The service controller interacts with cloud providers for load balancers, and many others. It's the engine that drives Kubernetes towards the desired state.
And speaking of cloud providers, there's also the Cloud Controller Manager. What's its specific role, especially in cloud environments like AWS, Azure, or GCC?
The Cloud Controller Manager, or CCM, plays a crucial role specifically when you're running Kubernetes on a public cloud. It basically acts as a bridge, linking your Kubernetes cluster with your cloud provider's specific APIs and services. For instance, when you create a Kubernetes service of type load balancer, it's the CCM's job to actually call the AWS, Azure, or GCP APIs to provision a real underlying cloud load balancer instance in your account. It also manages things like cloud provider storage volumes or node lifecycle integrations specific to that cloud.
So it keeps Kubernetes itself cloud agnostic.
Exactly. By abstracting away the cloud-specific implementation details into the CCM, the core Kubernetes control plane components can remain largely generic and unaware of the specific cloud they're running on. It's a key part of Kubernetes' portability promise.
Okay, so from the brain, the control plane, let's move to the muscles, the components running on every single worker node. Sticking with our hotel analogy, these are the hotel rooms themselves and the diligent staff who work within them, primarily the kubelet and kube proxy. They are the ones actually hosting the guests or running the pods and containers. So, expert, what does the kubelet actually do on each node? It sounds critical.
Oh, it's absolutely critical. The kubelet is essentially the primary node agent, the real workhorse on each individual worker node in the cluster. It's the component that makes a machine a Kubernetes node. It constantly communicates with the API server. Its main jobs are getting the pod specifications, the desired state, that have been scheduled to its node, and then ensuring the containers described in those pod specs are actually running and healthy.
How does it do that? Does it run the containers itself?
No, it doesn't run them directly. It interacts with the container runtime, like container to the thaw, that's also running on the node.
Yeah.
It tells the runtime to pull the necessary container images, start the containers, stop them, etc., based on the pod spec. It's also responsible for mounting the volumes defined in the pod into the containers, reporting the health of the node and the status of the pods back to the API server, and executing those crucial container health probes.
And speaking of health, Kubernetes container probes are absolutely essential for building resilient applications. We typically hear about three main types: liveness probe, readiness probe, and startup probe. How do they differ, and why are all three potentially vital, especially at scale?
They're all vital for different aspects of application reliability, and using them correctly is key. The liveness probe checks if your container is still alive and fundamentally functioning. Is it stuck in a deadlock? Is the process hung? If the liveness probe fails consecutively, the kubelet assumes the container is deadlocked or broken and restarts the container. It's about automatic recovery from internal failures.
Okay, restarts on failure. What about readiness probe?
The readiness probe determines if your application within the container is actually ready to serve traffic. Maybe the process is running, so a liveness probe passes, but it's still initializing, loading data, or temporarily overloaded. If the readiness probe fails, the pod's IP address is removed from the endpoints list of any Kubernetes services it belongs to.
So traffic stops flowing to it.
Exactly. It prevents traffic from being sent to an instance that's not ready to handle it successfully. This is crucial during application startup, rolling updates, or when an instance is temporarily unhealthy but might recover.
And the third one, startup probe.
The startup probe is specifically designed for applications that take a long time to start up initially. Sometimes complex apps might need minutes to become fully ready. If you set aggressive liveness or readiness probes, the kubelet might restart the container before it even had a chance to finish starting.
So it gives it more time at the beginning.
Precisely. The startup probe runs first. Once it succeeds, then the kubelet starts using the liveness and readiness probes. It essentially disables the other probes during that initial startup window, preventing premature restarts for slow-starting apps.
How do these probes actually check the application?
There are three main ways. You can configure an exec probe, which runs a specific command inside the container, like cat teamhealthy. If the command exits with status 0, it's success. You can use HTTP GET, which makes an HTTP GET request to a specific path and port on the container. A 2XX or 3XX response is success. Or you can use TCP socket, which simply tries to open a TCP connection to a specified port. If it connects, it's success. Using these effectively is crucial for automated health management.
Okay, kubelet manages the pod lifecycle and probes. What about kube proxy? What's its role on the node?
Kubeproxy is all about networking, specifically implementing the Kubernetes service concept. Remember, services provide a stable IP address and DNS name for a set of pods. Kubeproxy, running on each node, watches the API server for changes to service and endpoint objects. It then translates these service definitions into actual network rules on the node itself. Its job is to make sure that traffic destined for a service's virtual IP address gets correctly load balanced and routed to one of the healthy backing pods for that service, wherever they might be running in the cluster.
How does it implement those rules?
Historically, it often used iptables rules on Linux nodes. This involves creating potentially many complex firewall rules. A more modern and often more performant mode is IPVS, IP Virtual Server, which uses a hash table structure in the kernel and is generally considered more scalable for clusters with a very large number of services. But fundamentally, its job is service discovery and load balancing at the network level on each node.
Okay, so kubeproxy handles service routing. You also mentioned the container runtime being present on the node. And for service discovery within the cluster, we rely heavily on DNS, right?
Absolutely. The container runtime is there, doing the low-level container management as instructed by the kubelet. And yes, Core DNS, or its predecessor kubedns, is the standard in-cluster DNS server. It's usually deployed as a regular deployment itself within the cluster. Its primary job is service discovery. When your application tries to connect to mybackend-svc.my-namespace.svc.cluster.local, Core DNS resolves that name to the stable cluster IP address assigned to the mybackend SVC service. This is the fundamental mechanism allowing pods to find and communicate with each other using stable names rather than ephemeral pod IPs.
Got it. Now, point of frequent confusion, monitoring metrics. We have the metric server and we have Prometheus. You mentioned Prometheus earlier. What's the crucial distinction between metric server and a full monitoring system like Prometheus? They sound similar.
This is a really important distinction to understand. A metric server is a relatively lightweight cluster add-on. Its primary purpose is to collect current resource usage metrics, primarily CPU and memory utilization, directly from the kubelets on each node.
Just current usage.
Yes, basically point-in-time data. Its main consumers are the Kubernetes Horizontal Pod Autoscaler, HPA, which uses these metrics to make automatic scaling decisions, and also the kubectl top node and kubectl top pod commands, which give you a quick snapshot of current resource usage. It doesn't store historical data.
Okay, so HPA and kubectl top. What about Prometheus then?
Prometheus is a much more powerful, full-featured monitoring and alerting system. It's designed to scrape metrics from various targets, like your applications, node exporters, etc., at regular intervals, and store that data as time series in its own database.
So it keeps history.
Exactly. Prometheus stores historical data, allowing for rich analysis, querying trends over time, using its powerful query language PromQL, building complex dashboards, and setting up sophisticated alerting rules based on that historical data. It's designed for deep operational insight.
And crucially, you said earlier, Prometheus does not scrape from metric server.
Correct. Prometheus does not scrape from metric server by default or by design. Metric server doesn't expose its metrics in a Prometheus-compatible format. Prometheus scrapes metrics directly from endpoints exposed by your applications, often a metrics path, from exporters like Node Exporter running on each node, and very importantly for cluster state, from kube state metrics.
Okay, so kube state metrics, or KSM, seems like a key component for Prometheus in a Kubernetes environment. What exactly does KSM provide that Prometheus scrapes?
Yes, kube state metrics is incredibly valuable for Prometheus-based monitoring of Kubernetes. It listens to the Kubernetes API server and generates metrics about the state of the Kubernetes objects themselves. So instead of application-level metrics or node resource usage, KSM gives you metrics like the number of desired replicas for a deployment versus the number currently available, the status of persistent volume claims, bound, pending, the phase a pod is currently in, running, pending, failed, the number of nodes ready in the cluster, and so on.
So it's metadata about the cluster state exposed as metrics.
Precisely. It translates the Kubernetes API object state into Prometheus metrics. It's designed specifically to be scraped by Prometheus. When you combine these KSM metrics with application metrics and node metrics and Grafana dashboards and Prometheus alerts, you get incredibly powerful visibility into the health, performance, and operational correctness of your entire Kubernetes cluster and the applications running on it. It's a critical piece for serious monitoring.
Networking in Kubernetes can definitely feel like a labyrinth sometimes, but it's absolutely essential for getting your applications talking to each other and the outside world. The service object is our fundamental way to get a stable endpoint for a set of ever-changing pods. Can you quickly outline the four main service types and their common use cases?
Sure thing. The service is key to abstracting away those ephemeral pod IPs and providing a stable way to access a group of pods performing the same function. The four main types are 1. Cluster IP. This is the default type. It assigns a stable internal IP address that's only reachable from within the cluster. Perfect for backend services, databases, caches, anything that doesn't need direct exposure outside the cluster.
Okay, internal only.
2. Node port. This type exposes the service on each node's IP address at a specific static port within a predefined range. Trafficating node IP. Node port gets routed to the service's cluster IP and then to the backing pods. It's sometimes used for development or demos, but generally not recommended for production due to port conflicts, firewall complexities, and lack of proper load balancing.
Right, seems awkward for production.
3. Load balancer. This is the standard way to expose a service externally, especially on cloud providers. When you create a service of type load balancer, Kubernetes, via the Cloud Controller Manager we discussed, automatically provisions an actual external cloud load balancer, like an AWS ELB or GCP load balancer, in your cloud account. This external LB gets a public IP and routes traffic into your cluster to the service's node ports or directly to pods, depending on the cloud provider implementation.
The standard for external access, then?
Generally, yes, for non-HTTP traffic or single services. 4. External name. This is a bit different. It doesn't deal with pods directly. Instead, it maps the Kubernetes service name to an external DNS name, like mymanaged-db.rds.amazonos.com. It essentially creates an internal alias within the cluster's DNS. This is useful for allowing internal applications to refer to external services using a consistent internal name without needing proxies.
Okay, load balancer type seems common for external access, but for HTTP and HTTPS traffic, especially when you have multiple microservices you want to expose, ingress is often mentioned as the preferred way. What's the core advantage of using ingress over, say, just creating a bunch of service-type load balancer objects, one for each web service?
The core advantage of ingress boils down to smarter Layer 7 HTTPS routing and cost efficiency. Instead of provisioning a potentially expensive external cloud load balancer for each and every HTTPS service you want to expose, ingress allows you to define rules for routing external traffic based on things like the requested host name, e.g. api.example.com via www.example.com, or the URL path, e.g. AP users via web. All this traffic typically flows through a single external load balancer that directs traffic to your ingress controller, which then uses these rules to route requests internally to the correct backend service and pods.
So one load balancer, many services.
It's significantly more cost-effective, especially at scale, and provides much more granular control for exposing multiple web applications or APIs through a unified entry point. It's the standard pattern for L7 traffic into Kubernetes.
And it's really crucial to understand the distinction between an ingress controller and an ingress resource.
Yeah.
I've seen people get tripped up by this. Can you clarify that for us? Because as you hinted, one doesn't work without the other.
Absolutely. Critical distinction. The ingress resource is just the configuration object you create in Kubernetes, typically a YAML file.
Sure.
It's purely declarative. It's where you define the rules like, I want traffic for host.api.example.com with path, v1 orders to go to the order service on port 8080. It's just data stored in, etc.
Just the
Right. The ingress controller is the actual engine, the piece of software, a pod or set of pods that's running inside your cluster. Common examples are NGINX ingress controller, Trafic, a proxy ingress, or cloud-specific ones like AWS Load Balancer Controller or GKE Ingress Controller. This controller constantly watches the Kubernetes API for ingress resources. When it sees one, it reads the rules and configures an actual reverse proxy, like NGINX or Envoy, based on those rules to handle the incoming traffic and route it correctly.
So you need both.
You must have an ingress controller deployed and running in your cluster to make ingress resources actually do anything. The resource is the desired state. The controller is the component that makes that state a reality by managing the underlying proxy and often the external load balancer configuration.
Okay, that clarifies ingress. Now, for security within the cluster, network policy acts as a kind of firewall for your pods at layer 3 and 4. Why is this so important, especially given that, by default, Kubernetes networking is pretty wide open? And what about controlling egress traffic leaving a pod?
Network policy is critical for security because, yes, by default in most Kubernetes CNI setups, all pods can communicate with all other pods across all namespaces. It's a flat network initially. This is often not desirable from a security perspective. Principle of least privilege. Network policy allows you to implement fine-grained network segmentation within the cluster. You can define rules that specify which pods are allowed to connect to which other pods, based on labels, namespaces, or even IP blocks. The common pattern is to implement a default deny model for a namespace block, all traffic by default, and then explicitly allow only the necessary ingress, inbound, and egress, outbound connections required by your application. This significantly reduces the potential blast radius if one component is compromised.
So you can control both incoming and outgoing.
Yes. You define ingress rules to control what can talk to your pods, and egress rules to control what your pods are allowed to talk to. Controlling egress is often overlooked, but is very important for preventing compromised pods from reaching sensitive internal systems or exfiltrating data.
Can you get even more granular with egress control?
You can get quite granular with network policy based on labels and ports. For even more advanced outbound control, especially when dealing with external services or needing features like TLS origination or L7 traffic monitoring for egress, you might look at solutions like an Istio egress gateway, which provides a dedicated policy-controlled exit point for traffic leaving the service mesh. But network policy is the foundational Kubernetes mechanism for L3-L4 isolation. Requires a CNI plugin that supports it, like Calico or Cilium.
Right. Now, moving up the stack from basic ingress, we often hear about API gateways. They seem to offer a more feature-rich single entry point than a standard ingress controller. This brings up an important practical question. Who does what when it comes to things like rate limiting, IP blacklisting, whitelisting, or maybe even authentication? Is that the job of the ingress controller, a service mesh like Istio, or a dedicated API gateway? What's the typical layered approach look like in a FA-ANG level setup?
That's a classic, it depends, but also a great question about layered security and traffic management. It's rarely just one component doing everything. Your ingress controller is typically good for basic edge functions. It can often handle basic IP whitelisting, blacklisting, maybe some simple rate limiting based on IP address, and of course TLS termination. It's the first line of defense at the cluster edge for general web traffic.
Okay, basic edge stuff. What about Istio?
Istio, or other service mesh, operates within the cluster, at the sidecar level next to your services. It excels at more sophisticated layer 7 policies between your microservices. Think fine-grained authorization based on JWT claims, mutual TLS enforcement for service-to-service encryption, advanced traffic splitting, retries, and potentially more sophisticated rate limiting based on service identity or request characteristics within the mesh.
So more internal service-to-service focused.
Generally, yes. Now, a dedicated API gateway, like Kong, Tyke, Apigee, or cloud provider services like AWS API Gateway, is typically used specifically for managing your public-facing APIs. It sits either in front of or sometimes replaces the ingress controller for API traffic. API gateways usually offer a much richer feature set geared towards API management. Things like complex user authentication and authorization offloading, OAuth, OIDC, API keys, sophisticated rate limiting and quotas per user or plan, request response transformation, API composition, combining multiple backend services into one API call, enhanced observability and analytics specifically for APIs, and even developer portals for API discovery and onboarding.
So it's often a layered approach.
Very often, yes.
Right,
You
yeah.
might have. 1, an API gateway handling external API traffic, applying business-level policies. 2, an ingress controller handling general web traffic and maybe routing to the API gateway or other web apps. 3, Istio handling internal service-to-service security, traffic management, and observability within the mesh. Each layer provides specific capabilities, working together for comprehensive control and security.
We briefly touched on the CNI plugin earlier, the container network interface for foundational pod networking. But now we've talked a lot about Istio handling advanced traffic management, MTLS, observability. Why do we still need CNI when we have something as powerful as Istio doing so much of the network magic? Isn't there some overlap, or could Istio replace CNI?
That's a great clarifying question because they operate at fundamentally different layers and serve distinct purposes. There's very little functional overlap, and Istio absolutely does not replace CNI. You need both.
Okay, so what does CNI do that Istio doesn't?
CNI provides the basic plumbing. The CNI plugin, like Calico, Cilium, Flannel, WeaveNet, is responsible for the foundational layer 3 and 4 networking within the Kubernetes cluster. Its core jobs are 1. Assigning an IP address to each new pod. 2. Creating the virtual network interface, like a VETH pair, for the pod, connecting it to the node's network namespace and the broader cluster network. 3. Ensuring basic IP reachability between pods across different nodes. 4. Optionally, implementing Kubernetes network policies for L3-L4 firewalling. Without a CNI plugin, your pods literally wouldn't get IP addresses or be able to communicate over the network at all. It sets up the basic connectivity fabric.
And Istio then builds on top of that.
Exactly. Istio operates primarily at layer 4 through layer 7. It assumes that basic IP connectivity provided by the CNI plugin already exists. Istio then injects its Envoy sidecar proxies, which intercept the traffic flowing over that CNI-provided network. Istio uses those proxies to add its advanced features: automatic mutual TLS encryption between services, sophisticated traffic routing and splitting, virtual services, resiliency features, retries, timeouts, circuit breaking via destination rules, fine-grained access control, authorization policies, and generating detailed metrics, traces, and access logs for observability.
So CNI for the roads, Istio for the smart traffic lights and security cameras on those roads.
That's a pretty good analogy, actually, yes. You absolutely need both working together. CNI lays a network foundation, and Istio builds the advanced application-level networking intelligence on top of it.
Okay, that makes sense. Beyond networking, let's talk configuration again, but this time focusing on sensitive data. We've covered config maps for non-confidential key value pairs with their cool live update capability via volume mounts. But for sensitive information passwords, API token certificates, we obviously need to use Kubernetes secrets. What's the critical difference in intent? And more importantly, what's a major security pitfall people need to be aware of with default Kubernetes secrets?
Right, the intent is clear. Secret objects are specifically designed for holding small amounts of sensitive data like passwords, OAuth tokens, SSH keys, TLS certificates. That's their sole purpose, differentiating them from config maps. However, and this is a major security pitfall that catches many people out, especially in less mature environments by default, the data stored within a Kubernetes secret object is only base 64 encoded when it's stored in, etc.
Base 64, that's just encoding, not encryption, right?
Exactly. Base 64 is trivial to decode. Anyone who can read the secret object from the Kubernetes API, which might be more roles than you think, or anyone who has access to the underlying etc. backups, can easily see the sensitive data in plain text. It provides zero actual confidentiality.
So what's the solution? How do you actually secure secrets?
To be truly secure, especially at an AVANG level where security is paramount, you must enable encryption arrest for secrets in your Kubernetes cluster. This is a feature configured on the Kube app server itself. It tells the API server to encrypt the secret data before writing it to etc., using a provider like a local key file, or ideally an external key management service, KMS, from your cloud provider. Only then is the data truly protected while stored persistently.
That seems absolutely essential for production. Okay, now related to secrets, but in the context of GitOps workflows, managing secrets in Git is always a challenge. A popular solution, especially in the Helm ecosystem, is Helm Secrets. It allows developers to commit encrypted secret values directly into their Helm charts in Git. This raises an important question that comes up a lot in high security environments. Helm secrets versus a more dynamic externalized solution like using Vault Agent Injector with HashiCorp Vault. Which approach is generally considered better or more appropriate for FANG level production applications? This feels like a significant trade-off.
This is a classic trade-off, pitting developer convenience and GitOps purity against the most robust security posture and operational capabilities. And generally, for FANG-level production systems handling highly sensitive data, the Vault Agent Injector pattern is considered superior, primarily due to its enhanced security, dynamic secret rotation capabilities, and better auditability.
Why is Vault Agent Injector more secure? Don't Helm Secrets encrypt the data in Git?
Helm Secrets does encrypt the data at rest in Git, which is good. It uses client-side encryption with various backends like PGP, KMS, or even Vault itself. However, the potential vulnerability lies in the CI/CD pipeline during deployment. To deploy the Helm chart, the CI/CD runner needs the decryption key. It decrypts the secrets in memory on the runner, renders the plain text Kubernetes secret manifest, and then applies it to the cluster. So, for a brief moment, the plain text secret exists on the CI/CD system, which increases the potential exposure surface. Keys also need to be managed for the CI/CD system.
Okay, a potential exposure point during CI/CD. How does Vault Agent Injector avoid that?
The Vault Agent Injector uses a Kubernetes mutating admission webhook, like Istio's sidecar injector. When a pod is created with specific annotations, the injector automatically adds a lightweight Vault Agent sidecar container to the pod. This sidecar authenticates directly with your Vault server at runtime, typically using the pod's own Kubernetes service account identity. It then fetches the required secrets directly from Vault and writes them to a shared in-memory volume mounted into the pod.
So the secrets never leave Vault in plain text during the deployment pipeline.
Correct. The secrets are fetched dynamically at runtime, directly by the pod itself. They never transit through the CI/CD system in plain text. This aligns much better with zero-trust security principles.
What about rotation and auditing?
Yeah, that's another huge advantage of the Vault Agent approach. The agent can automatically keep secrets fresh by refetching them from Vault periodically based on their TTL, time to live, and rewriting them to the shared volume. Your application just needs to be able to reload them from the file. This enables seamless, automated secret rotation without needing a full pod redeployment. Vault also provides detailed audit logs of exactly which identity accessed which secret and when. Helm secrets, being static in Git, makes rotation a manual commit and deploy process.
So, Vault Agent Injector seems better for high-security, dynamic environments, but maybe a bit more complex to set up initially.
Exactly. Helm secrets is simpler to get started with, especially if you're already heavy into Helm and GitOps. Vault Agent Injector requires running and managing Vault itself, though managed cloud options exist, and understanding the injection mechanism. But for applications demanding the highest level of security, dynamic rotation, and clear audit trails, typical FAANG requirements, the Vault Agent pattern usually wins out.
Okay, that clarifies the secrets management trade-offs. Now, almost every application needs storage that persists beyond the lifecycle of a single pod. Let's delve into persistent storage in Kubernetes. It's handled through several layers of abstraction, which can be a bit confusing at first. First, we have persistent volume, or PV, and persistent volume claim, or PVC. What are they, and how do they interact?
Right. These two objects work together. Think of the persistent volume PV as the cluster administrator's view of storage. It represents an actual piece of storage provisioned in the cluster, maybe an AWS EBS volume, a GCP persistent disk, an NFS share, or a Ceph volume. A TV is like a resource in the storage inventory of the cluster. Crucially, it has a life cycle independent of any individual pod.
So the admin provisions the storage, creates a PV object for it. What's the PVC then?
The persistent volume claim, PVC, is the developer's request for storage. It's defined within a specific namespace, just like a pod. A developer creates a PVC specifying their requirements. I need 10 GB of storage that supports read-write-once access. The PVC acts like a request that Kubernetes tries to fulfill by finding a suitable, available PV in the cluster that matches the requested size and access modes. Once a match is found, Kubernetes binds the PVC to that PV.
And then the pod uses the PVC.
Exactly. The pod definition then references the PVC by name in its volume section. Kubernetes ensures that the specific PV bound to that PVC is mounted into the pod when it starts. This decouples the pod from the specifics of the underlying storage. The pod just asks for storage via the PVC.
That sounds like static provisioning the admin creates PVs first. What about creating storage on demand? That seems more cloud native.
You're absolutely right. That leads us to the real magic for modern cloud native storage, the storage class. Storage classes enable dynamic provisioning, which is almost always the preferred method in cloud environments because it's fully automated.
How does it work?
Instead of pre-provisioning PVs, the administrator defines one or more storage class objects. Each storage class describes a type or class of storage available, maybe fast SD, standard HDD, backup storage, and specifies which underlying storage provisioner should be used for it. Then when a developer creates a PVC, they simply reference the desired storage class name in the PVC definition. For example, storage class name, fast SSD.
And Kubernetes creates the storage automatically.
Yes. When the PDC is created referencing a storage class, Kubernetes triggers the specified provisioner associated with that storage class. This provisioner, which is often implemented using a CSI plugin, then automatically calls the underlying cloud provider API, like AWS EC2 or GCP Compute Engine, to provision a brand new storage volume matching the PVC's request on demand. It then creates the PV object of that new volume and binds the PVC to it.
CSI plugin. What's that?
CSI stands for Container Storage Interface. It's the modern standard way for storage providers to integrate their systems with Kubernetes and other container orchestrators. It defines a standard API for how Kubernetes talks to storage systems to perform actions like creating volumes, deleting volumes, attaching them from nodes, unmounting them, taking snapshots, etc. CSI decouples the storage provider logic from the core Kubernetes code. This means storage vendors can develop their own CSI drivers independently, allowing for immense flexibility and innovation in storage solutions for Kubernetes without needing changes in Kubernetes itself. It's the standard now.
So dynamic provisioning via storage class and CSI is the way to go in the cloud. Got it. Okay, let's shift gears to CI/CD and DevOps in a FAANG level Kubernetes environment. Tools like Jenkins are still quite popular, often running in a clustered master agent architecture. How does that typically work with Kubernetes?
Jenkins remains a workhorse. In Kubernetes, a common pattern is to run the Jenkins master, or controller as it's called now, as a deployment itself. Then, instead of having static build agents, you configure Jenkins to use the Kubernetes plugin to dynamically provision Jenkins agent pods on demand within the Kubernetes cluster whenever a build job starts.
So build agents are ephemeral pods.
Exactly. Each build runs in a clean, isolated pod configured with the necessary tools, JDK, Maven, Docker client, etc. When the build finishes, the agent pod is terminated. This is highly scalable and efficient. And modern Jenkins heavily emphasizes defining your build pipeline as code using a Jenkins file, which is typically stored alongside your application code in source control.
Speaking of source control, GitHub, or perhaps Bitbucket, usually serve as the central hub for code management. How do they integrate with the CI/CD process?
They're fundamental. Source code management systems like GitHub or Bitbucket are where your application code, your Docker files, your Kubernetes YAML manifests, your Jenkins files, everything lives. They integrate tightly with CI/CD tools like Jenkins, primarily through webhooks. When a developer pushes code or opens a pull request, GitHub can automatically trigger a webhook notification to Jenkins, which then kicks off the corresponding build, test, and maybe even deployment pipeline. The whole pull request workflow, where changes are proposed, reviewed, automatically tested by CI, and then merged, is central to modern DevOps practices. And platforms like GitHub Actions are increasingly popular as an alternative or complement to Jenkins for CI/CD, running workflows directly based on repository events.
And where does something like GRA fit into this picture?
JRA, or similar tools like Azure DevOps boards, is typically the issue tracking and agile project management tool. It acts as the system of record for work. Developers link their commits and pull requests back to specific JRA tickets. This provides full traceability. You can follow the lifecycle from a user story or bug report in JRA and the specific code changes in GitHub through the CI/CD pipeline build logs in Jenkins, all the way to the deployed artifact in Kubernetes. This traceability is crucial for auditing, compliance, and understanding the impact of changes.
Okay, the pipeline runs, tests pass, the image is built. Now comes the deployment to production. When it comes to deployment release strategy in K8s, we often hear canary deployments are considered the gold standard for safety, especially compared to other strategies. Can you quickly compare the common strategies and explain why canary is preferred at scale?
Sure, there are a few common strategies, each with trade-offs. 1. Recreate. This is the simplest but most disruptive. It terminates all old pods before starting any new ones. This causes downtime and is generally only suitable for development environments.
Definitely not for production.
No way. 2. Rolling update. This is the default strategy for deployments in Kubernetes. It gradually replaces old pods with new ones, ensuring zero downtime if configured correctly, losing readiness probes. However, if the new version has a bug, it might still affect a significant portion of users before you can react and roll back. The blast radius can still be large during the rollout.
Better, but still some risk.
Right. 3. Blue-green deployment. Here, you deploy the entire new version, green, alongside the entire old version, blue. Production traffic points to blue. Once green is tested and ready, you instantly switch the router, like a service selector or ingress rule, to point all traffic to green. Rollback is equally fast, just switch back to blue. The downside is it requires roughly double the infrastructure resources during the deployment.
Instant switch, but costly. And canary.
Canary deployment. This is generally considered the safest approach for releasing critical applications at scale because it significantly limits the blast radius of a potentially bad deployment. Instead of switching all traffic at once, you first deploy the new version, the canary, alongside the stable version, and route only a small percentage of live user traffic to it, maybe 1%, 5%, or 10%.
Just a small test group.
Exactly. You then closely monitor key metrics, error rates, logs, and maybe even user feedback specifically for the canary instances. If everything looks good, you gradually increase the traffic percentage shifted to the canary, maybe 25%, 50%, eventually 100%. If any issues arise at any stage, you can immediately roll back traffic away from the canary back to the stable version, impacting only that small percentage of users.
That sounds much safer. How does a service mesh like Istio make implementing canaries easier?
A service mesh like Istio simplifies canary deployments immensely because it provides powerful, fine-grained traffic shifting capabilities right out of the box, controlled declaratively via its virtual service resources. You can easily define rules like send 95% of traffic to pods with label version stable and 5% of traffic to pods with label version.canary. See both there. You could even do more sophisticated routing, like sending only specific users based on headers or cookies to the canary. Trying to achieve this level of precise, percentage-based traffic splitting reliably at the network level without a service mesh is significantly more complex, often involving multiple deployments, services, and manual adjustments. Istio makes it a standard, manageable pattern.
Okay, Canary is the way for safe releases, potentially powered by Istio. Once our applications are running, how do we actually know what's going on inside them? That's where observability comes in. We often talk about the observability pillars being metrics, logs, and traces. We've already discussed Prometheus as the de facto standard for monitoring metrics in Kubernetes. Can you recap its pull-based model and how that data scraping actually works? Is data buffered first, or is it immediate storage?
Right, Prometheus uses a pull-based model. This means the Prometheus server itself actively reaches out and pulls or scrapes metrics data from configured HTTP endpoints on its targets at regular intervals, for example, every 15 or 30 seconds. These endpoints typically expose metrics in a specific text-based format, often at a metrics path.
So Prometheus initiates the connection.
Yes, it pulls the data directly from the target when it scrapes. It's not typically buffered by the application specifically for Prometheus first. The scrape data, along with the timestamp of when the scrape occurred, is then immediately ingested and stored in Prometheus's own internal time series database, TSDB.
And it keeps that data for how long?
You configure the retention periods for the TSDB, for example. You might configure Prometheus to keep 15 days or 30 days of historical metrics data. Prometheus handles the storage and eventual purging of old data based on that retention setting. Its core components, remember, include the Prometheus server with the scraper, TSDB, and query engine, various exporters to expose metrics from systems that don't natively support the Prometheus format, an alert manager for handling alerts, all powered by that PromQL query language for retrieving and analyzing the stored time series data.
An alert manager is a separate component that Prometheus talks to. What does it do?
Yes. Alert managers typically run as a separate component. Prometheus evaluates alerting rules based on the metrics data it collects. When an alert condition is met, Prometheus fires that alert to Alert Manager. Alert Manager then takes over, handling tasks like deduplicating alerts if the condition persists, grouping related alerts together, inhibiting certain alerts based on others, say, gee, don't alert on individual app instances if the whole cluster is down, silencing alerts temporarily during maintenance, and routing the finalized notifications to the correct destination like Slack, PagerDuty, email, etc. It adds a crucial layer of intelligence on top of Prometheus's basic alerting capabilities.
For visualizing all this Prometheus data, Grafana seems to be the go-to tool.
Absolutely. Grafana is the leading open-source visualization platform, and the Prometheus plus Grafana stack is the classic, incredibly powerful combination for monitoring Kubernetes and applications. Grafana connects to Prometheus as a data source, lets you build rich, interactive dashboards using PromQL queries, and visualize trends, statuses, and alerts in a user-friendly way.
Can you manage those dashboards easily?
Yes, a best practice emerging is dashboards as code. You can define your Grafana dashboards declaratively using JSON models or tools like Grafana JSONit, store them in Git, and automatically provision them into Grafana, making your monitoring setup reproducible and version controlled, just like your infrastructure.
What about logs? Prometheus is mainly metrics. For enterprise logging, Splunk is a huge player. How does it typically fit into a Kubernetes environment? Is it competitive with Prometheus Grafana?
Splunk is a very powerful commercial platform, primarily focused on logs, but it also handles metrics, events, and security information. CM. It's often used in large enterprises for centralized logging, compliance, and security analysis. In a Kubernetes context, the common pattern is to deploy a log forwarder agent like Fluent, FluentBit, or the Splunk Universal Forwarder, often as a daemon set on every node. This agent collects container logs, usually from Stouter, captured by the container runtime in Kubelet, and potentially application log files from volumes, formats them, adds Kubernetes metadata, like pod name, namespace labels, and then forwards them securely to a central Splunk instance, which might be running on-premises or in the cloud.
So it complements Prometheus rather than competes directly.
Often, yes. While Splunk can ingest metrics, Prometheus is generally considered the stronger, purpose-built solution for time series metrics monitoring in the Kubernetes ecosystem. Many organizations use Prometheus Grafana for real-time operational metrics and alerting, and Splunk for deep log analysis, searching, troubleshooting, and longer-term retention for compliance and security forensics. They serve different primary purposes, but could be integrated, e.g. linking from a Grafana dashboard to relevant logs in Splunk. The main difference is also cost, and architecture Splunk is commercial and often involves significant licensing costs based on data volume, while Prometheus Grafana is open source.
Looking towards the future of instrumentation, OpenTelemetry, or OTel, seems to be gaining a lot of momentum. It promises to unify metrics, logs, and traces. How does OTel address the problem of vendor lock-in for observability data? That sounds like a big deal.
It is a big deal. OpenTelemetry is a CNCF Cloud Native Computing Foundation project, and it's rapidly becoming the industry standard for instrumenting applications to generate telemetry data. Its core goal is to unify the collection of all three observability pillars: traces for understanding request flows, metrics for aggregated measurements, and logs for event records. It solves the vendor lock-in problem by providing a standardized vendor-neutral set of APIs, SDKs, software development kits for various languages, and wire protocols. The idea is you instrument your application code once using the OpenTelemetry APIs and SDKs.
Instrument once, send anywhere.
Exactly. Your application then emits telemetry data, traces, metrics, logs, in a standardized format, OTLP, OpenTelemetry Protocol. From there, you typically deploy the OTel collector, a flexible agent or service, which can receive this OTLP data, optionally process or enrich it, and then export it to multiple different observability backends simultaneously. So you could easily send your traces to Jaeger, your metrics to Prometheus, and your logs to Splunk or Loki, all from the same instrumentation just by configuring the OTel collector. It gives you incredible flexibility to choose best-of-breed tools or switch vendors without having to re-instrument all your applications. It decouples instrumentation from the back-end analysis tools.
That sounds incredibly powerful for long-term strategy. Now back to Prometheus specifically. To make configuring Prometheus scrapes easier, especially at scale with lots of services, the Prometheus operator introduces custom resources like Service Monitor and Pod Monitor. What do these do?
The Prometheus operator is a fantastic tool for managing Prometheus instances within Kubernetes using Kubernetes native practices. Instead of manually configuring Prometheus scrape targets in a static config file, the operator introduces these CRDs, Service Monitor and Pod Monitor. A Service Monitor tells the operator how to discover and scrape metrics endpoints exposed by Kubernetes services. You typically create a Service Monitor that selects services based on labels. The operator then automatically generates the necessary scrape configuration for Prometheus to find and scrape all the pods backing those selected services. Similarly, a pod monitor allows you to directly select and configure scraping for specific pods based on labels, bypassing the service layer if needed.
So it automates the scrape config generation?
Yes, precisely. It makes managing Prometheus scrape configuration much more dynamic and Kubernetes native. You define these simple CRD objects alongside your application manifests, great for GitOps, and the operator handles the complex task of keeping the Prometheus configuration up to date as services and pods come and go. It's the standard way to run Prometheus effectively at scale within Kubernetes.
And for visualizing the service mesh specifically, if you're using Istio, Kiali is the tool for that.
Correct. Kiali is an observability console specifically for Istio. It consumes the telemetry data generated by Istio via Prometheus and potentially Jaeger for traces, and provides a graphical interface to visualize your service mesh topology. You can see how services are connected, view traffic flow, error rates, latencies, and even visualize Istio configuration objects like virtual services and destination rules applied to your services. It's invaluable for understanding and troubleshooting complex microservice interactions within an Istio mesh.
Okay, observability covered. Finally, no FANG level system is complete without rock-solid security. This is always a multi-layered approach, as we've touched on. Let's start with access control within Kubernetes. RBAC, or role-based access control, is the standard. It involves 4 key object types: role, cluster role binding, and cluster role binding. Can you break those down, maybe using an analogy?
Sure. RBAC is the fundamental mechanism for controlling who can do what within your Kubernetes cluster. The analogy often used is job descriptions and assignments. Role and cluster role define the job descriptions. They specify a set of permissions verbs like get, list, watch, create, delete, update, applied to specific Kubernetes resources like pods, deployments, secrets. A role is namespaced. Its permissions apply only within a specific namespace. A cluster role is cluster-wide. Its permissions can apply to cluster scope resources like nodes or to namespace resources across all namespaces.
So role, cluster role define what actions are allowed on what resources. What about who gets those permissions?
That's where role binding and cluster role binding come in. They're the job assignments. They bind a role, or cluster role, the job description, to a specific subject, which can be a user, a group, or most commonly for in-cluster processes, a service account. A role binding grants the permissions defined in a role, or a cluster role, to subjects within a specific namespace. A cluster role binding grants the permissions defined in a cluster role to subjects across the entire cluster. Using these 4 objects together allows for very granular control over permissions, adhering to the principle of least privilege.
Speaking of subjects, what about Kube API authentication? How does the API server verify who is making a request in the first place before RBAC even kicks in? And I have a specific question here. Do we need to manage certificates inside each pod for them to talk to other Kubernetes services or the API server itself?
Good question on authentication. The API server supports several authentication methods configured by the cluster administrator. Common ones include 1. Client certificates, used by components like the kubelet and sometimes by human administrators. The API server verifies the client cert against a trusted CA. 2. Static token file, a simple CSV file mapping tokens to usernames. Less common now. 3. Bootstrap tokens, special tokens used for securely joining new nodes to the cluster. 4. Service account tokens. This is the primary method used by processes running inside pods. Kubernetes automatically creates a JWT JSON web token for each service account and mounts it into pods using that service account. 5. OpenID Connect OIDC tokens. This is the standard way to integrate with external identity providers like Google, Okta, Active Directory via ADFS for authenticating human users accessing the cluster. For example, is VQPickle. The API server validates OIDC tokens against the external provider. Now, to answer your specific question, no, you generally do not need to manage certificates inside each pod for standard in-cluster communication or talking to the API server.
So how do pods authenticate then?
Pods almost always use those automatically mounted service account tokens. When a library inside your pod, like the official Kubernetes client libraries, needs to talk to the API server, it reads this token from the standard file system path. Var secrets kubernetes.io service account token, includes it in the authorization. Bearer token header of the API request. The API server then validates this JWT token to identify the service account making the request. RBAC rules are then applied based on that service account identity, so it's token-based for pods, not certificate-based typically.
Okay, that clarifies pod identity. For security monitoring and forensics, Kube audit logs sound crucial. What do they capture?
Kube audit logs are absolutely critical for security, compliance, and troubleshooting. They provide a chronological record of every single request made to the Kubernetes API server. For each request, they log details like who made the request, user service account, what action they tried to perform, verb, what resource they targeted, pod, secret deployment, where it came from, source IP, when it happened, and crucially, what the outcome was, success, failure. You configure an audit policy to control how much detail is logged. Metadata only, request body, response body. Analyzing these logs is essential for detecting suspicious activity, investigating security incidents, and meeting compliance requirements. They need to be shipped securely off cluster for analysis and retention.
So they see everything. What about intercepting requests before they hit, etc.? We mentioned admission controllers earlier in the context of Istio sidecar injection. Can you elaborate on their role as gatekeepers for the cluster? What's the difference between mutating and validating?
Admission controllers are powerful gatekeepers that intercept requests to the Kubernetes API server after the request has been authenticated and authorized by RBAC, but before the object has actually persisted into, etc. They act as a final checkpoint. There are two main types that could be implemented via dynamic webhooks. 1. Mutating admission webhook. These controllers can actually modify the object being created or updated. The classic example is Istio's sidecar injector, which adds the onboard container definition to your pod manifest on the fly. Other uses include automatically adding labels, setting security contexts, or injecting environment variables. 2. Validating admission webhook. These controllers can only validate the object, they cannot change it. They review the request and can either approve it, allowing it to proceed to etc., or reject it with an error message if it violates some defined policy. Examples include ensuring all images come from a trusted registry, enforcing specific label requirements, or checking for security best practice violations using policy engines like OPA Gatekeeper or Kyverno. These dynamic webhooks make Kubernetes incredibly extensible, allowing organizations to enforce custom policies and automation deeply integrated into the API flow.
We talked about service account as the identity for processes and pods. Best practice is obviously least privilege. Give each application only the permissions it absolutely needs via RBAC bindings. What about namespace? It provides logical isolation, but what does it actually isolate? And importantly, what does it not isolate by default?
Namespaces are a fundamental way to organize resources within a Kubernetes cluster. They provide a scope for names. A pod named myapp in namespace dev is different from myapp in namespace prod. They also provide a scope for applying RBAC rules via roles and role bindings, and resource constraints, resource quotas. So you can isolate permissions and resource usage between different teams, applications, or environments using namespaces.
But what don't they isolate?
The key thing namespaces do not isolate by default is networking. As we discussed earlier, by default, a pod in namespace A can freely communicate over the network with a pod in namespace B. They also don't isolate nodes or underlying cluster infrastructure. If you need network isolation between or even within namespaces, you absolutely need to implement network policies. Namespace provides organizational and policy scoping, not network barriers by default.
Okay, and you mentioned resource constraints within namespaces. We have resource quota and limit range. They sound similar, both deal with resource limits. What's the crucial distinction between them? When would you use one versus the other?
This is a common point of confusion, but they serve distinct complementary purposes for resource governance. Resource quota operates at the namespace level. It limits the total aggregate amount of resources that can be consumed by all pods and other objects within that entire namespace. For example, you can set a resource quota saying the dev namespace can use a maximum total of 10 CPU cores and 32 gigabytes of memory across all its pods, or can only have a maximum of 50 services or 100 secrets. It puts a ceiling on the namespace's overall consumption.
So namespace totals, what about limit range?
Limit range operates at the individual pod or container level within a namespace. It constrains the resource requests and limits that can be set on individual containers. For example, you can use a limit range to 1. Enforce minimum and maximum CPU memory requests or limits per container. For example, no container can request more than 2 CPU cores. 2. Specify default CPU memory requests or limits if a container doesn't define its own. Crucial for ensuring pods get a quality of service class. 3. Enforce a ratio between requests and limits.
So limit range controls individual container sizes. Resource quota controls the namespace total.
Exactly. Think of it like resource quota sets the total budget for the namespace, while limit range sets rules for the size of individual items purchased within that budget. You typically use both together for effective resource management. Limit range ensures sensible defaults and constraints on individual pods, while resource quota prevents any single namespace from hogging all the cluster's resources.
Okay, we've covered a huge amount of ground, from the basics up through core components, networking, storage, security. Now let's talk about the sophisticated layer that truly enables massive scale, advanced traffic control, and deep observability, especially in complex microservice architectures. The service mesh, with Istio often cited as the leading implementation. Expert, just a level set, what exactly is a service mesh, and how does Istio achieve its magic with that distinct control plane and data plane architecture?
Right, a service mesh is essentially a dedicated infrastructure layer built right into your application network to make service-to-service communication, the traffic between your microservices, safe, fast, and reliable. It takes responsibility for handling things like reliable delivery, security, and observability for all that internal traffic. Istio, as the leading open-source choice, implements this using a clever separation of concerns. 1. It has a control plane, primarily the Istio component. This is the brain. It doesn't touch the application data packets directly. Its job is to manage and configure all the proxies in the mesh, aggregate telemetry, and provide APIs for operators to define policies. 2. It has a data plane, which is composed of high-performance Envoy sidecar proxies. These are deployed alongside each instance of your application containers, typically within the same pod.
Envoy again. So these sidecars intercept traffic.
Precisely. The magic is that these Envoy proxies intercept all inbound and outbound network traffic to and from your application container. They do this transparently. Your application code doesn't need to change. It just talks over the network as usual. Istio, the control plane, dynamically configures these Envoy proxies via APIs, like XDS, telling them how to handle the traffic based on the policies you've defined, like virtual services, destination rules, authorization policies.
And what are the main benefits you get from this?
The key benefits are significant. Traffic management, sophisticated routing rules for canary deployments, A/B testing, gradual rollouts, fault injection, request timeouts, retries, all configured centrally without touching app code. Security, automatic mutual TLS, MTLS, encryption and identity verification for all service-to-service traffic within the mesh. Fine-grained authorization policies based on service identity or request attributes, like JWT claims. Observability, consistent, detailed metrics, the golden signals, latency, traffic, errors, saturation, distributed traces, and access logs generated automatically by the Envoy proxies for all traffic, giving you deep visibility into your microservice interactions. It basically extracts all that complex cross-cutting networking concern out of your application code and into a manageable platform layer.
It sounds incredibly powerful. And you mentioned admission controllers earlier. Istio uses them for something critical in its setup, right? How do those sidecars actually get there?
Absolutely. Istio deeply leverages Kubernetes mutating admission webhooks for seamless integration. When you label a namespace for Istio sidecar injection, Istio injection enabled, a webhook configured by Istio intercepts every pod creation request within that namespace. This mutating webhook automatically modifies the pod manifest before it's saved to, etc., injecting the definition for the Istio proxy, Envoy container, and any necessary init containers right into your application's pod spec.
So it happens automatically at deploy time.
Yes. This enables transparent sidecar injection. As a developer, you just deploy your application YAML as usual, and Istio automatically adds the sidecar proxy needed to bring your service into the mesh. You don't have to manually edit your deployment YAMLs to include the proxy container. It's a very elegant integration.
Is there a way to see Istio in action easily?
Yes, the Istio project provides a sample microservices application called the Book Info application. It's specifically designed to demonstrate Istio's core features like traffic routing, fault injection, MTLS, and telemetry collection in a practical way. Deploying Book Info is usually one of the first steps when learning Istio.
Okay, and for controlling traffic leaving the mesh, you mentioned an egress gateway earlier. What about internal changes in Istio, like Istio Telemetry v2? And what's this gateway API that's supposed to be the future?
Right, an egress gateway in Istio provides a dedicated controlled exit point for traffic originating from within the mesh that needs to reach external services outside the Kubernetes cluster. Instead of letting every pod talk directly out, you route outbound traffic through this central gateway, allowing you to apply consistent policies like TLS origination, traffic monitoring for all external communication. Istio Telemetry v2 represents the modern architecture for how Istio collects its observability data. The older architecture relied heavily on a component called Mixer, which became a performance bottleneck. Telemetry v2 moved much of this logic directly into the Envoy proxies themselves, often using WebAssembly WASM extensions. This significantly improved performance and scalability by processing telemetry closer to the source.
WASM and Envoy, interesting. And the gateway API, is that replacing Ingress?
The Gateway API is a newer official Kubernetes API. It's graduating through alpha, beta, GA stages that aims to provide a more expressive, flexible, role-oriented, and vendor-neutral way to model service networking configuration, particularly for ingress, getting traffic into the cluster, but also potentially for mesh traffic too. It addresses many of the limitations and ambiguities of the original Ingress API. It separates concerns more clearly between infrastructure providers, defining gateway classes and gateways, and application developers, defining HTTP routes, TCP routes, etc. Istio has strong support for the Gateway API, and yes, it's widely seen as the future of ingress and potentially service networking configuration in Kubernetes, eventually likely superseding the Ingress API for most use cases. Adoption is growing rapidly.
Okay, the future is Gateway API. We've talked a lot about the Envoy sidecar proxy being the core of the data plane. Can you just reiterate its role in that injection mechanism? And then how do Istio's main traffic routing resources, virtual service, and destination rule work together? It sounds like they're often used in tandem.
Absolutely. The sidecar proxy, which in Istio's case is Envoy, is that high-performance C++ proxy sitting next to your application container. Its role is to intercept all inbound and outbound network traffic for that application. It's the enforcement point for all the policies defined in the control plane. It gets its configuration dynamically from the Istio control plane, Istio via the XTS API, X-Discovery Service APIs. This API tells Envoy about services, routing rules, security policies, etc. And the sidecar injection mechanism, as we discussed, is typically handled automatically by that mutating admission webhook, adding the Envoy container to your pods. Now, virtual service and destination rule are the two fundamental Istio resources for configuring how that intercepted traffic is routed and handled. They work hand in hand. 1. A virtual service defines the routing rules for traffic destined for a particular service within the mesh. It answers the question, where should requests for this service go? This is where you configure things like traffic shifting, splitting traffic between different versions of a service. For example, 90% to V1, 10% to V2 for a canary release. Request routing. Routing based on HTTP headers, URL paths, source labels, etc. E.g., send a request with header user agent timing. Mobile to the mobile optimized version. Fault injection. Intentionally introducing delays or errors for testing resiliency. Retries and timeouts. Configuring retry policies and request timeouts.
So virtual service decides where it goes. What does destination rule do?
A destination rule configures policies that apply to traffic after the routing decision has been made by the virtual service. It defines how to talk to the actual destination pod instances selected by the routing rule. Key features configured in a destination rule include load balancing policies, how to distribute traffic among the instances, using round robin, least connections, random, connection pool management, Settings for TCP and HTTP connection pools, example, max connections, timeouts. TLS settings, client-side TLS settings when initiating connections to the service, fancily enforcing MTLS. Outlier detection. This is Istio's implementation of circuit breaking. It allows Envoy to detect unhealthy instances, for example based on consecutive errors, and temporarily eject them from the load balancing pool, preventing cascading failures.
So virtual service for where, destination rule for how to talk to the where.
Exactly. You almost always need both. Virtual service defines the high-level routing logic, and destination rule configures the low-level connection and endpoint policies for the subsets defined or routed to by the virtual service.
We also have an Istio Gateway CRD, which is different from the Kubernetes Gateway API object, right? And for security, pure authentication configures mutual TLS-MTLS mode, while authorization policy provides fine-grained access control.
Correct. The Istio Gateway CRD is specifically for configuring Envoy proxies running at the edge of the mesh, typically in an ingress or egress gateway deployment. It defines the L4, L6 properties like ports, protocols, and TLS settings for traffic entering or leaving the mesh. It often works together with a virtual service bound to it to control routing from the edge. It's Istio's native way of handling edge traffic configuration. And yes, for security within the mesh, pure authentication defines the mutual TLS mode for services receiving traffic. You can set it to strict, only MTLS allowed, permissive, allow both MTLS and plaintext, or disable, only plaintext. This is typically set mesh-wide or per namespace. Authorization policy provides fine-grained access control after MTLS authentication. It lets you define rules specifying who, which source principal service accounts, namespaces, IP blocks is allowed to access what, which services, methods, paths based on various conditions, including validating JWT claims. It's Istio's RBAC system for service-to-service communication.
And we've covered core patterns enabled by these. Traffic shifting for Canaries AB, automatic MTLS for encryption in transit, using SPIFE A identities for strong workload identity, fundamental resiliency patterns like retry, timeout, and circuit breaking via outlier detection, and even rate limiting capabilities often implemented via Envoy extensions. That's a huge amount of functionality the mesh provides. Beyond the service mesh itself, Kubernetes offers powerful ways to extend its core functionality, which many of these tools leverage. The custom resource definition, or CRD, seems absolutely fundamental here. What does it allow?
CRDs are perhaps one of the most powerful features of Kubernetes. They allow you, or third-party vendors, to extend the Kubernetes API itself by defining your own custom object types beyond the built-in ones like pods, deployments, and services. Once you define a CRD, for example, defining a new kind called database cluster, you can create, read, update, and delete instances of that custom object using standard kubectl commands and the Kubernetes API, just like built-in resources.
But the CRD itself doesn't do anything, right? It just defines the new type.
Correct. The CRD just tells the Kubernetes API server about the schema of your new object type. To actually make that custom object do something useful, you need to write a custom controller, often called an operator. This combination, a CRD defining the custom object plus a custom controller operator that watches for changes to those objects and takes actions to reconcile the desired state, is known as the operator pattern. This is how tools like Istio, with its virtual services, destination rules, etc., the Prometheus operator, with service monitors, database operators, managing database clusters via CRDs, and countless other Kubernetes extensions are built. It makes Kubernetes incredibly extensible.
And building on that operator pattern, Cluster API, or CPI, uses it to manage Kubernetes clusters themselves.
Yes, Cluster API, KPI, is a Kubernetes subproject that takes the operator pattern to the next level. It aims to manage the lifecycle of entire Kubernetes clusters using Kubernetes itself. It defines a set of CRDs representing cluster components like cluster, machine deployment, machine, Kubernetes control plane, etc. You then run TBI controllers, operators, in a management cluster, and you could declaratively define the desired state of your workload clusters by creating instances of these KPI CRDs in management cluster. The KPI controllers then interact with underlying infrastructure providers, AWS, Azure, GCP, vSphere, Bare Metal, to provision and manage the workload clusters according to your declared state.
So Kubernetes managing Kubernetes.
Exactly. It provides a single, consistent, declarative, API-driven way to manage fleets of Kubernetes clusters across potentially any environment. It's a very powerful abstraction for organizations running many clusters.
Okay, before we wrap this massive deep dive up, let's try to address some of the big practical questions about how all these different pieces fit together in a real world, complex, maybe FANG level environment. For example, the Java ecosystem is huge and Spring Boot is incredibly popular for building microservices. Does Spring Boot work seamlessly with Kubernetes? And maybe more pointedly, if you're using sophisticated platform tools like Istio for traffic management, Consul for service discovery, Vault for secrets, what's even left for frameworks like Spring Boot or maybe Spring Cloud to do? It feels like the platform takes over so many responsibilities.
That's a great observation, and it really highlights a significant architectural shift that platforms like Kubernetes enable. First off, yes, absolutely. Spring Boot works beautifully with Kubernetes. It's a fantastic framework for building the actual microservice application logic that runs inside the container managed by Kubernetes. Now, what's left for Spring Boot when the platform provides so much? If core responsibilities remain focused on the business logic, it's still responsible for implementing your REST TGB RPC endpoints, handling serialization, JSON, protobuf, performing business validation, managing data access, interacting with databases via JPA, JDBC, etc., providing dependency injection, a core Spring feature, and crucially, exposing observability endpoints like Spring Boot Actuators, Actuator Health, Actuator Prometheus endpoints that the platform tools, Kubelet Probes, Prometheus, can consume.
So the core application logic is still in Spring Boot. What about Spring Cloud?
This is where the bigger shift happens. Many concerns that Spring Cloud modules traditionally address things like client-side service discovery, Eureka, console client, distributed configuration, Spring Cloud config server, circuit breakers, Hystrix, resilience 4-day, API gateway patterns, Spring Cloud Gateway, can now often be handled externally by the platform layer. Istio provides service discovery, sophisticated circuit breaking, retries, and traffic management. Kubernetes config maps or Vault provide configuration and secrets. An external API gateway handles edge routing. So you often don't need to include those specific Spring Cloud dependencies in your application anymore. You can run plain Spring Boot applications, focusing purely on the business domain logic, and let the Kubernetes Istio Vault platform handle the distributed systems heavy lifting.
So developers can focus more on business value.
That's the goal. Externalize the infrastructure complexity to the platform. You'll still use Spring Boot's application.aml or application.properties for some application-specific configuration, but a lot of the environment-specific or infrastructure-related configuration now comes from config maps, secrets, or Vault injected into the application at runtime.
That's a huge paradigm shift for developers used to fat frameworks. Okay, another common challenge. Integrating with backend services or external systems that often run outside the Kubernetes cluster. Think large existing Oracle RAC databases, enterprise Apache Kafka clusters, maybe legacy IBM MQ systems, or even artifact repositories like Nexus. How will my Kubernetes microservices connect and work reliably with these external systems as if they were just another part of the application?
That's a very common integration scenario in large enterprises. There are several robust methods to bridge the gap between your Kubernetes cluster and these external systems. One, Kubernetes external name service. As we mentioned, if the external service has a stable DNS name, you can create an external name service inside Kubernetes that acts as an internal alias. Your internal apps connect to the service name, and kubedns resolves it to the external DNS. Simple, but just DNS aliasing. Two, Istio service entry. If you're using Istio, a service entry is the way to formally register an external service within the Istio service mesh. This allows you to apply Istio policies like MTLS origination, traffic rules, telemetry collection to traffic going to that external service, making it feel like a first-class citizen of the mesh. 3. Network connectivity, VPN, VPC, peering direct connect. For secure, reliable, low-latency connectivity, you often need to establish proper network links between your Kubernetes cluster's VPC, virtual private cloud, and the network where the external system resides. This could be via VPN tunnels, cloud provider VPC peering, or dedicated interconnects like AWS Direct Connect or Azure Express Route. 4. Sidecar proxies for protocol translation offloading. Sometimes you might deploy a dedicated sidecar proxy alongside your application, specifically to handle communication with a legacy external system, perhaps translating protocols or offloading authentication complexity. 5. Vault agent for external secrets. If your Kubernetes app needs credentials to connect to an external database or service, the Vault Agent sidecar can securely fetch those credentials from Vault and provide them to your application. 6. Console for external service discovery KV. If the external systems are registered in Console, your Kubernetes applications can use Console clients or Console DNS to discover them or fetch configuration from Console's key value store. The goal is usually to abstract the location difference away from the application code as much as possible, making those external systems accessible via stable internal names or configurations managed by the platform.
You mentioned HashiCorp Console and Vault. They're often used together. Just to clarify, are Console and Vault themselves considered persistent volumes? And a big architectural question. Generally, for FANG level production, are Vault and Console servers deployed outside of the Kubernetes cluster or inside it?
Good questions. First, no, Console and Vault are applications, not persistent volumes themselves. However, when you deploy Console or Vault servers, the stateful components, within Kubernetes, they absolutely do require and use persistent volumes via PVCs to store their data persistently, Console's cluster state or Vault's encrypted secret storage. Now, for the deployment location in production, the strong, widely accepted recommendation for large-scale, high-availability, multi-cluster environments is to run the Vault servers and Console servers outside of any single Kubernetes workload cluster.
Run them externally. Why?
There are several key reasons. Isolation. Running them externally isolates these critical infrastructure components from the lifecycle, potential failures, or security compromises of any single Kubernetes cluster. If the cluster goes down, your central secrets management and service discovery remain available. Multi-cluster support. A single external Vault or Console cluster can securely serve multiple Kubernetes clusters, and potentially non-Kubernetes workloads too, providing a unified control plane for secrets and discovery across your entire organization. Bootstrapping. It simplifies the bootstrapping process for new Kubernetes clusters, as they can immediately connect to the existing external Vault console for secrets and configuration. Security posture. It allows you to manage and secure these highly sensitive servers with potentially stricter controls separate from the general workload clusters.
So you run the servers externally. How do the applications inside Kubernetes use them?
You then run lightweight Vault agents, as sidecars or init containers, and Console clients, often as a daemon set providing DNS or sidecars, inside your Kubernetes clusters. These agents securely connect back to the external Vault Console servers to fetch secrets, register services, perform health checks, or retrieve configuration. This gives you the best of both worlds: robust, isolated servers, and seamless integration for your in-cluster applications.
Okay, Vault and Console servers outside. What about Prometheus deployment? Is the Prometheus server itself typically run inside Kubernetes or outside in these large environments?
For Prometheus, the recommendation is generally the opposite of Vault Console. For most use cases, especially when the primary goal is monitoring the Kubernetes cluster itself and the applications running within that cluster, it's recommended to deploy the Prometheus servers inside Kubernetes.
Why inside for Prometheus?
Running Prometheus inside the same cluster it's monitoring offers several advantages. Simplified service discovery. Prometheus can leverage Kubernetes' native service discovery mechanisms via the API server to automatically find pods and services to scrape based on labels and annotations, especially when using the Prometheus operator and service monitors. Configuring this from outside the cluster is much harder. Network locality. Scraping happens over the internal cluster network, which is typically faster and doesn't require exposing metrics endpoints externally or complex network configurations. Native integration. It can easily use standard Kubernetes persistent volume claims for storing its time series data. Resource management. Its resource usage can be managed using standard Kubernetes requests and limits. Deploying Prometheus outside the cluster is less common and usually only considered for specific scenarios, like building a highly federated metrics aggregation layer that collects data from many disparate clusters, or in environments with extremely strict network segmentation requirements where running monitoring agents inside is prohibited. But for monitoring a given cluster, inside is typically the way to go.
Okay, that clarifies the typical deployment locations. Now, let's try to bring this all together. Can you sketch out a high-level view of a FANG level production architecture, showing how a request might flow and how these key components interact?
Okay, let's trace a typical request flow in such an environment. It's all about layers and clear responsibilities. 1. A client request from a user's browser, mobile app, or another system usually first hits an edge API gateway, like Kong, Apigee, or cloud provider's managed gateway. This gateway handles initial authentication, maybe OAuth or ADC, applies coarse-grained rate limiting, performs basic validation, and potentially routes the request based on API path or version. 2. The API gateway often forwards the request to an Istio ingress gateway running inside the Kubernetes cluster. This gateway is the entry point to the service mesh. It terminates TLS, potentially applies edge security policies, WAF integration, and uses Istio gateway and virtual service rules to route the request to the appropriate internal microservice.
Free. The request arrives at the target service, a Kubernetes service object, which load balances it to one of the backend pods. 4. Inside the pod, the request is intercepted by the Envoy sidecar proxy. Envoy enforces any relevant Istio policies, like authorization policy, MTLS checks if applicable from the gateway, circuit breaking, fine-grained rate limiting, and collects detailed telemetry, metrics, traces. 5. Envoy then forwards the request locally, via localhost, to the application container running in the same pod, for example, your Spring Boot app. 6. The application processes the request. It might read its configuration from mounted config maps or dynamically fetch secrets provided by a Vault agent sidecar talking to an external Vault server. 7. If the application needs to call another internal microservice, it makes a network call to that service's Kubernetes service name. This outbound call is again intercepted by its Envoy sidecar, which handles service discovery via Istio's service registry, performs load balancing according to destination rule policies, enforces MTLS for secure communication, and collects telemetry for the outbound call. 8. If the application needs to connect to an external system, like an Oracle database or Kafka cluster running outside Kubernetes, the connection might be routed through an Istio egress gateway, potentially using connection details discovered via console or credentials fetched from Vault. The network path itself relies on the underlying VPC peering VPN. Meanwhile, the entire lifecycle of these pods and deployments is managed by the Kubernetes control plane. Kube App Server, etc., Kube Scheduler, Kube Controller Manager. On the worker nodes, the kubelet manages pods and containers via the container runtime, Kube Proxy handles service routing, and the CNI plugin provides the fundamental pod networking. For observability, Prometheus, running inside the cluster, likely managed by Prometheus Operator, scrapes metrics from Envoy sidecars, application endpoints, Actuator Prometheus, Node Exporter, Daemon Set, and Kube State metrics. Alert Manager processes alerts fired by Prometheus and routes notifications. Grafana visualizes all these metrics in dashboards. Kiali visualizes the Istio service mesh, traffic, and configuration. Log forwarders, Fluent, Bitfluent, Daemon Set, collect logs from all containers and ship them to a centralized logging system like Splunk or Loki Elasticsearch for analysis and retention. Distributed tracing, if enabled via Istio and application instrumentation with OpenTelemetry, sends trace data to a backend like Jaeger. And underpinning everything is security. Istio's automatic MTLS, authorization policies, Vault for secrets management, Kubernetes RBAC for API access control, network policies for L3, L4 segmentation, admission controllers for policy enforcement, and Kube audit logs for forensics. It's a complex system, but each component has a well-defined role, working together to provide a resilient, observable, secure, and scalable platform. The key insight is how much of this infrastructure complexity is externalized from the application itself, allowing developers to focus more on delivering business value.
Wow, what a truly comprehensive deep dive. That was amazing. From the absolute basics of containers all the way up to securing and observing these incredibly complex multi-cluster, multi-component environments, we've really unpacked the intricate layers that make these FANG level systems hum. The key takeaway for me, at least, is just how much Kubernetes and its incredibly rich ecosystem allow you to externalize so much of that heavy lifting, the networking, security, observability, resiliency patterns. It really lets your applications focus purely on their core business logic. It feels like a fundamental paradigm shift in how we build and operate software at serious scale.
Absolutely. But connect this all back to the bigger picture. It's really about enabling organizations to build these highly resilient, deeply observable, and fundamentally secure systems by design, rather than trying to bolt these capabilities on as an afterthought. The platform provides the foundation, and this, I think, raises an important question for you, our listener, to consider as you reflect on everything we've discussed today. Where do you see the greatest opportunity to apply some of these advanced concepts, maybe service mesh, maybe better secrets management, maybe observability to your own projects or within your own organization? And perhaps, what single component or pattern, if you were to implement it well, do you think would yield the most significant improvement in your current architecture? Something to really chew on.
That's a fantastic challenge to leave everyone with. Food for thought indeed. Keep exploring, keep learning, keep building. Thank you so much for joining us on this incredibly detailed deep dive today. It was fantastic. Until next time, stay well informed.